There's a
computer somewhere too.
Yeah, what about this? Okay, great. Yeah, I really do it anything I do. You do this if I do it, right? Right.
So was it 13-5A?
3A.
3. 3A. Okay.
And B?
That's right. Okay, we jumped forward, but we were still working on that. Okay. So the idea was, shoot, I just erased the whole thing. But we took a triangle. That was a right triangle. We created an altitude, which broke the hypotenuse into two pieces. This altitude is the height, and we separate it. This height here in this space, so we take this, we turn it, because this angle is the same as this angle. And then what we're able to do is we're able to write that proportion, which takes us to this. And the height is what's called the geometric mean. It's a geometric mean because, without going into a lot of detail, this is a size change we multiplied to go from this to this. And when we change things geometrically, we do it using multiplication. Like if I have numbers as such, to go from this number to this number, you multiply by 4. And then to go from 16 to 64, you multiply by 4. So that's what it is it's a constant ratio. So the ratio between these two numbers here is the same as between these two numbers here. 16 to 4 is like 64 to 16. How? Because a ratio, I guess if I had a triangle that was 4 and 16, and I just made this bigger by 4 times, I'm going to make this length bigger by 4 times. Now they're similar. So I can take numbers and apply them to a triangle. Numbers from there's a sequence where we just keep multiplying by 4. You know, the next one would be 4 times 64, and then times 4, and times 4, and times 4. That's what's called a geometric sequence. And when we're comparing similar figures, that's a geometric comparison. Because each dimension has the same thing happening to it. This is multiplied by 4. This is multiplied by 4. So let me write it again. 16 is to 4 as 64 is to 16. lot of information there, isn't there? But numerically, geometrically, same here. Because we can write this ratio as such. And we saw things that were similar. So this is 90, this is 90. So that's the basis of the whole geometric mean. The property or theorem or what, but how it works, that's the basis of it right there. So then it's a matter of trying to find if this relationship exists in a figure, and then identifying the different lengths. And that's what the problems were asking us to do. Did any of you find 7 to be challenging?
Yes.
I did too. I want to erase that right away. I don't know if anybody wants that. Probably author's statement.
It's 13.9.
This would be the
So it's an isosceles right triangle with the legs of 2 is perpendicular to IX. So that takes us into this relationship. But it looks a little weird because it doesn't tell us this length or this length, does it? And it doesn't tell us the altitude either. But it does tell us it's an isosceles triangle. So what else, well, what would we know from that statement, do you think? This is probably going to be the only one I do, by the way.
that IM and MS are equal,
IM and MS are equal.
and then so will, then OM will be equal to the length of IM or MS.
So those two are equal because it's isosceles.
And then OM is equal to those, to that one length we find for both of those.
So OM is equal to what?
The length we find for MS or MI.
This. Okay, well, we got, what we would normally do is, if we wanted to orient it like this, we'd say the altitude is equal to each of these portions multiplied together, but then the square root of it. Hi. Do you have it? Okay.
Should I go out and open it?
You can talk to Mrs. Dagan, she'll work with you on that, okay? So that altitude is equal to this times this, but that altitude is equal to these two multiplied by one another, but then the square root of their product. So, you know, we struggled through this one last night a little bit. And can I just call that H? Can we just do that?
Yeah.
So OM is equal to H. So now that height is equal to the square root of MI times MS. MI is equal to MS. Or MS is equal to MI, it doesn't matter, same. So if I substitute, if we substitute it and we say that it's equal to MI times MI, that's equal to the square root of MI squared. Probably nicer with parentheses. So then the square root of a square is equal to the root. So that's OM or MO. So OM is equal to MI, which is equal to MS. What's really wild about that, we were doing it last night, and we drew it. Because this is like a 90-degree isosceles triangle. These are each 45. So we drew it. We drew an altitude, drew another altitude, and we found out every single one of these new triangles is similar. This is unique. And this is why Mrs. Dagan had a couple of you stop when you started with your free drawing the other day, when you had a 45, 45, 90, and she had you make something that was other than 45, 45, 90, just because if it would have been like this, it would have been kind of a different relationship that you'd been seeing. That you wouldn't have noticed that there was a square root in there, at least not as clearly. So then let me ask you, what other questions would you want to have me go over?
Can you not find the actual lengths of MI and MS?
Can you?
Yeah.
Well, let's see here. Ooh. Did you find them?
Yeah,
Whole length of the other side.
I just found it using the Pythagorean of the big one and then divided that answer by 2, which gave me IM. And then I can substitute that in for MS and OM.
Did you get 2 for them?
I got 1.4.
So we said that OM is equal to MS, which is equal to MI.
For IS, I got 2.8.
Really?
About.
Okay. You know what? This might be a good time to give this to you. I think this is a good time. Don't you think? Yeah. I've been thinking about this. I was wondering when I can give you this one. This is worth scribbling down in your notebook.
For what chapter? Or what lesson?
I don't know. It's the end of the year. It's everything I'm trying to jam into the last 2 days. We could think of it as being a part of the next lesson, I guess. It's a little bit of an extension, but I think it's a good thing to see. And we've seen some of this already, right? Yeah, what am I thinking? So you started out with something that's like this, right?
Yeah.
And we knew that MI and MS were going to be equal to each other. So they would each be half of that hypotenuse. So how would you find the length of the hypotenuse given the 2 legs being 2? Pythagorean, yeah. So let's just call this x. So then we've got 4 plus 4 equals 8. So now this has to be how long? Square root of 8. Okay, so what is the square root of 8 if we simplify the root and leave it as an exact value? 2 root 2. Yeah, because this is 2 times 4 underneath the radicand. Take out the square root of 4. So it's 2 root 2. So how long is this? Just along here. That's half of that. What's half of 2 root 2? Root 2. It's root 2 divided by 2, which is root 2. So then when you do this, how long is this altitude? What's this angle here? 90. It's isosceles, so what does this length have to be? Square root of 2. And this is the square root of 2. So, you can check yourself, does this fit the Pythagorean? The square root of 2 squared plus the square root of 2 squared should be equal to 2 squared. Square root of 2 squared is 2. Square root of 2 squared is 2. 2 squared is 4. 2 plus 2 is 4. Good, it works. You could do that all day. Keep cutting them in half, but we'll stop there. Because there's another isosceles here that has this hypotenuse of root 2. But this is unique because it's a 45, 45, 90. If that 90 wasn't there, if you just had any isosceles triangle like this, then we can't do any of this at all. And if we have right triangles like that, we don't have equal legs either. So this is a unique, very unique situation. So from that lesson, Master, were there any other problem numbers that you wanted input as to how to get through? Okay, because if there was, we would do it, but we'd record it and send it to you, or put it out. So then I'm going to assume that we're good with this. And then let's move on. Let's go on to, you give this a lesson number. The world is starting to get mixed up. Oh, you're sitting on it. Yeah. So this is kind of 13.5 and 13.6. And I don't know, what about 4? I guess we're skipping it, or we did it, one or the other. But that, what's that? Oh, that was the golden ratio. Yeah, sorry. We're skipping golden ratio. We decided to do that. Figuring it'd be more important to have this introduced to you a little bit, because I'm figuring that most all of you are going to be in physics next year. And when you get into physics, what's her name? Yes, you can take physics. You should take physics. Tannehill? Yeah. Miss Tannehill. She will be real happy if you have seen sine, cosine, and tangent before. Because in many situations, physics will be done like in big schools. It'll be done with Algebra 2 and on up students. And we can't do that here. So she's got to do a little bit of teaching of some of the math, and I want to make sure I've got this much done for you going into that class. And if you're apprehensive about taking it, I can't urge you to take it enough over physical. Yes. It'll just be great. Be a great class to be in. So we had the tangent of an angle yesterday, we said was equal to the opposite over the adjacent. Is it okay if I abbreviate opposite and adjacent?
Yeah.
Okay, good. And just to make a picture so that we can look at this, if we choose that angle to be theta, then this is the opposite side. Did that yesterday. This is the adjacent. And there's the hypotenuse. And it's got to be for right triangles and right triangles only. But then there's two other relationships. There's sine and cosine. And sine gets abbreviated SIN, as you see on your calculator. And what the sine ratio is the opposite compared to the hypotenuse. So then, the last one is cosine. And the cosine is the adjacent. So we're talking the same angle yet, but we're picking up different ratio of side length. So this compares the adjacent to the hypotenuse. So those are the three relationships. And when you look at a problem, if there's not a sketch, make a sketch. And then identify as many pieces of the sketch as possible. Usually your sketch will be a right triangle. If it is, you get to use one of these, if there's enough information. But of course, we can really only have one variable. And the types of problems we're going to be throwing at you will be when one of these side lengths is not known. And then, no, I'm sorry, yeah, one of the side lengths is not known, but the angle has been given. So you can work forward like that. There are ways to find the angle if you just know that ratio. It's an inverse function. Maybe we'll touch on it on Monday, but that's not my first and foremost. So, if you were given the flagpole, which had a 50-foot shadow, and this angle was, I think I said 40 degrees yesterday. And for some weird reason, you knew this distance. And so I'm going to change the plan a little bit here, but maybe you knew that that was 75 feet. Now, in terms of a right triangle, what is the missing piece? The opposite side. So which of these would you want to use? Opposite's missing. So what can you do?
We want to eliminate that 50.
Do we? Okay.
And we never saw that.
Yeah, we can do that. We can say we didn't know it was there. That's fine. So now you have the opposite missing. You have the adjacent missing. You're right, thank you. That makes it so we can get this done in one quick shot. But what do you know? You know the hypotenuse. So you got this taken care of, and you know the angle, so you have theta taken care of. So if you needed to know how far away you were, you could find the adjacent length. So one relationship would be the cosine of 40 degrees is going to be equal to this missing side, call it x, over 75. And then you just solve it algebraically. What?
Are we trying to find the height?
Yeah, to find the adjacent side. Yeah, I'm sorry. This gives you the adjacent side.
Oh, okay, sorry.
Yeah, that's fine. So this would give you the adjacent side. What if you wanted to find the height? Then you need sine. Yeah, it's not sin, it's sine. Because you know the hypotenuse, you know the angle. So then what you can do is you can write the sine of 40 degrees is equal to the opposite, call it y, divided by 75. So if you solve that problem, then you figure out what the height is. So the key is that you know two of the three variables. There.
What are the two lines in between this?
I'm sorry?
What are the two lines in between this?
Oh, this is just separating this from this. Yes?
So what makes the two equations different?
Ooh.
Do they look similar and just because we're missing both of the numerators? Because because like from the board, they look exactly the same, but is that just because we're missing?
Yeah. What's different is that cosine is a function, it's a mathematical function that relates an angle measurement to a ratio. So it's a way of taking that angle and doing math to it to make it into a ratio. Sine is a different function. It takes and works the numbers differently, and then it gives you the ratio of this side to the hypotenuse. So the easiest way to say where does all that math come from is if you sat down very, very carefully and drew every triangle from 1 degree all the way up to 89 degrees, and you measured their legs. If you could do that very accurately, then you would have a whole table of information to refer to. And back when we were in school, that's how we did it, because we didn't have calculators that would do it. So we had tables of all the different angle measurements in the back of the geometry book. And that's where we would find the ratios of specific angles. So when you go and type in, for example, grab your calculator, and you go in and you do tangent of 45 degrees. 1. So that just means that the ratio of the opposite to the adjacent side is a 1-to-1 ratio. And if you were to put in something like the tangent of 30 degrees, that would be the ratio of these two legs here, opposite over adjacent. So if you took this measurement and divided it by that measurement, you would get, how much is it about? 0.58, yeah. And usually we pick up 3 decimal place values or 4. Yes?
So after you find that number, how do you use it? Like, you find a number, what do you do with it?
This here,
Or in any of those cases?
Yeah.
Do you just say, I found this fancy number, or how do you apply it in other problems?
no, let's say that you found that this is 0.58. That would mean that if the opposite side was 0.58, that this adjacent side would be 1. Well, what if I made my triangle so that this was twice as long? Then this side has to be twice as tall. If I made it 3 times as long, it would be 3 times as tall. So then what we can do is we can bring in the idea of similar triangles to make measurements from here to the stars.
And can you do that with all the things, or just with all of them?
Yeah, with all of them, as long as you know different parts of this. So what we first need to do is get used to using this and thinking about the language. And then you'll get word problems that'll have more meaning. And like in physics class, this just goes on and on and on with its importance and its use, and in the sciences. So, yeah, a couple of days ago, you were doing some pretty complicated geometry. Now we're back to training wheels again.
Yeah.
But these are training wheels that will propel you forward.
I forgot like 2 seconds on that.
Oh, yeah, look at this. Hey,
So, 13.5A.